All right, we've kind of gotten to one of the most important things we do all year. This is a sort of a culmination of all the things you've learned, not only in the chemical reactions unit, but all year. We're putting a lot of the pieces that we've learned together to predict products now for chemical reactions. A lot of these cases, you're going to be given some reactants, and it's going to be your job to identify the type of reaction you're being hinted at, and then to go ahead and make the products. I have 4 videos that I'm going to make. We're going to group synthesis and decomposition together, and then we're going to have separate videos for single, double, and combustion respectively. Before I do examples for each type, I want you to refer to the predicting products flowchart. You should have this in your notebook. If not, go to your Google Classroom and print it off. This is a very good guide for you to work through these problems. If you have yours out, go to the bottom of the flowchart where you'll find synthesis reactions. On the left-hand side is the clue that you look for in your reactants to see if you have a potential synthesis reaction, a combination of 2 compounds or 2 elements. Not the most helpful. Really, I think synthesis is probably the hardest for students to do. If you do identify it as a synthesis reaction, on the right it is suggested that there are 4 types of synthesis reactions. The first type is when you combine free elements to make binary compounds, and we're going to see lots of examples of those in a few minutes. But that would also include your diatomic elements. Those are free elements like Cl2, chlorine, H2 for hydrogen, O2 for oxygen. And it would also include other nonmetals that don't come as singular atoms, such as phosphorus comes as P4 in its most common allotrope, or sulfur comes as S8 in its most common allotrope. And those are just some things you have to learn with experience. The next type I want you to look out for is metal oxides plus water. That's just what it sounds like, metal oxide. Any metal with oxygen. It could be calcium oxide, sodium oxide, even really iron oxide, although that reaction is pretty slow. They make bases. Metal oxides plus water make metal hydroxides, which we know as bases. Then the third type would be non-metal oxides, such as sulfur dioxide, nitrogen dioxide, carbon dioxide, so on and so forth. Any non-metal with oxygen, you put those in water, you're going to make ternary acids, our oxyacids that we've learned about. And then the final type is how to make a ternary salt. If you react that metal oxide with a non-metal oxide, for example, calcium oxide is a metal oxide. Carbon dioxide is a non-metal oxide. If you react those two under the correct conditions, you will make calcium carbonate, which is a ternary salt. So we're going to see some examples of how to do that. But first, let's scroll up to the top of the predicting products flowchart and let's look at decomposition. I'm grouping these two together because they are exact opposites of each other. Each of those 4 types of compounds that I told you that we could just make, I can reverse it in a decomposition. If I take that binary compound, decompose it, I get my free elements back. If I take that base, that metal hydroxide, decompose it, I get my metal oxide and water back. The same for the ternary acid. Decompose it, get my non-metal oxide and water back. And you can see the same for the ternary salt. Okay, so let's get our worksheet out now and let's go through how to do some of these synthesis and decomposition reactions. Well, here we are with our practice. Now, the tools that you're going to need for this, of course, that flow chart, but you're going to need your periodic table, your solubility rules, anything like polyatomic ions, anything like that you may want to reference. At any time, hit pause and find those tools if you're not sure what I'm doing. But any of this putting elements or compounds together usually involves charges. So we're going to be, I'm going to go through here pretty fast, hoping that you understand where I'm getting these charges from to make my compounds. We're going to use charges to identify what subscripts are needed to build our compound. Okay, we're not worried about balancing as we build compounds. we will then balance later to obey the law of conservation of mass. So let's take a look at number 1 here. We have strontium plus oxygen. Those are both free elements. This is the first and simplest type of synthesis reaction. So before I put those together, it's not necessarily just going to be SrO2, like making a sandwich. I have to consider the charges that these elements are going to have. So from your periodic table, strontium is an alkaline earth metal and will be +2. Oxide, we know, is going to be -2. It's just one singular O. So with that, we put Sr and O together, not O2, Sr and O. Now, we are going to put states of matter in, and we're going to assume standard conditions unless we're told otherwise. So strontium's a metal, solid. Oxygen's a gas. And then, unless we have other information about water environment, this is an ionic compound and will also be a solid. Obviously, it's not balanced, so we will fix that by putting a 2 in front of strontium oxide and then a 2 in front of strontium. Now at the end of this, I don't want those charges to be there. I just have them there right now to let you know that I'm considering charges as I build my compounds. So that is my final answer. The charges should not be shown. Now as I move forward, I am going to write the charges in just for your benefit so you can see that I'm considering the charges before I build my compound. On to number 2, sodium and oxygen. Those are again free elements. So I know that sodium is +1, oxide will be -2. This time it'll be Na2O. And that would also be a solid. We'll go back and put our states of matter here. And then we need to balance that with a 2 here for the oxygens, and then a 4 for the sodiums. All right, number 3, potassium and chlorine, +1, -1. Those are what those two elements' charges would be. So those would go right together to make KCl, not KCl2, KCl, which would be a solid. Chlorine's a gas and a solid. All right, last one of these free elements coming together for binary compounds. Now, calcium is +2, fluorine would be -1, fluoride would be -1. So those do happen to come together, and it looks like we're just making a sandwich, but that's a consequence of a +2 -1 combination. And that would be solid virtually no matter what. Fluorine's a gas, calcium's a solid. So those are fairly easy, free elements coming together to make binary compounds. Now as we keep going, we're going to start with some words here, sort of like a skeleton equation, but we're going to go ahead and predict the products eventually. Sodium metal, solid, plus iodine, liquid. So for some reason we're told iodine's a liquid here. That is still a free element combination to make a binary compound. We will make NaI, +1 -1. And then balance. Okay, magnesium metal in number 6, we know is Mg. We all know that oxygen gas is diatomic. Another free element combination. Mg is +2, we know that oxide is -2. This compound, magnesium oxide, MgO. And it'll be a powdery solid. We saw that earlier in the year when we did it in our lab. Number 7, we have 2 free elements, but they're both diatomic, so don't forget that. And now in this case, hydrogen is your cation, it'll be +1. Our compound will be HCl. We'll go ahead and balance it because let's talk about the state of matter. This looks like hydrochloric acid, but in this case it's not. We do not have a water environment. So this is the gas form of HCl, and it would just be hydrogen monochloride, or most people just call it hydrogen chloride gas. Remember I told you before, acids have to be aqueous to be acids. All right, watch number 8. We have silver metal, And then sulfur powder. Sulfur is one of those elements I told you that come in an allotrope that's not a single element. Sulfur is commonly S8. And a powder would be a solid. Now, should you know that? No, you probably don't know that, but that part of this exercise is learning little things like that. It's probably not going to be the end of the world if you don't remember it, but that's what it is. Now, silver is +1. We know that from our alzenag mnemonic. Sulfur is still going to be -2. So the combination would give us Ag2S, silver sulfide. And that would require a good bit of balancing. 8 in front of silver sulfide, which means I need 16 silver atoms. That's it for the binary compounds being synthesized. In 9 and 10, we're going to go down to some of the other types. Number 9, calcium oxide, CaO, +2, -2. That is a metal oxide. From our flow chart, metal oxides, when we react those with water, we said earlier, give us bases. It's going to be a metal hydroxide. And the metal here is the calcium. So we just need to put calcium with hydroxide. So from your polyatomic ion list, if you've forgotten, hydroxide is -1, so we will need 2 of them. Now this is a water environment, so we use Cashingia to determine if this ionic compound will be solid or aqueous. Calcium hydroxide is a strong base. It will be aqueous. And I'm just double checking, yes, we are balanced, so we're good to go on that one. All right, number 10 is a different type of synthesis. Sulfur trioxide, from our covalent naming rules, is a nonmetal oxide. And if we react that with water, our flow chart said that our product will be a ternary acid. These are a little tricky for you to do. You got to think a little bit here. What kind of ternary acid? Well, let's just think out loud for a second. If I add this oxygen over here, remember oxygen is O-2, that kind of makes SO4 -2. So in a way, think about we're making sulfate. And now we just put the hydrogens in front of sulfate. So the ternary acid that we're going to make here is sulfuric. Again, water environment, sulfuric acid. All right, if you have any questions about the top 10, make a note of them, but we're about to move on to the decomp. Decomposition reactions are the easiest for you to recognize because there will be a single reactant. Your job is then to just identify the type of reactant according to what the flowchart suggests. For example, is it a binary compound? Is it a metal hydroxide? Is it a ternary acid, or is it a ternary salt? Let's go through 11 through 15 and just kind of practice that. Number 11, 2 elements, that is a binary compound. 12, same thing, binary compound. 13, even though it's not ionic, it's still 2 elements, binary compound. Same with 14, and then the same with 15. So let's do 11 through 15. It says binary compounds decompose to give us the free elements. We don't just take this stick and snap it in half. We have to think about what these elements are, or what they look like when they are by themselves. Number 11. Magnesium bromide will break up into its free elements, which would be magnesium, which comes as an atom. And then bromine actually is diatomic. And we learned way back in the periodic table unit that it's a liquid in its normal state. So this one gave us the appearance of just breaking apart. Watch number 12, it will not work out that way. Number 12, if we break this one up, we get aluminum, which is a solid. So far, so good. But we are not going to get Cl3. Chlorine comes in nature as Cl2. So that's what I mean by our product did not just look like we snapped AlCl3 in half. We had to write down what chlorine actually looks like in nature. Now we're going to fix that by balancing it. So I need, make the odd even, put a 2 here. And then we'll need a 3 here. and then a 2 in front of aluminum to keep it balanced. All right, number 13, we have water. If we decompose water, and by the way, these decomposition reactions usually are endothermic. They would require some type of energy, so maybe number 12, we had to add heat. Maybe number 13, heat's not enough, so we may have to add some electricity. Usually you need to be told exactly what's happening. So on number 13, if we break water up through electrolysis, we'll get H2 gas and then oxygen gas. Again, we didn't just snap it in half. We had to think about H and O and how they appear in nature. We would fix that with a 2 here and then a 2 here. All right, we'll do 14 and 15 really quickly here. We're going to make potassium solid, and then iodine is diatomic. I'm not going to lose a lot of sleep if you put solid or gas here for iodine. We've learned this year that it sublimes really quickly. And then 15, we're going to get sodium, and then we'll get that chlorine, which is diatomic, and it's a gas. I forgot to balance number 14, so let's go back and do that with a 2 and a 2, and then I need to do the same thing for 15. There we go. So those are the binary compound decompositions. Number 16 and 17 are going to be different types of compounds. These are going to be the last box under the decomposition. These are going to be ternary salts. Nickel 2 chlorate looks like this. So there is the ternary salt. And then copper 2 carbonate looks like that. They're ternary salts because they're 3 elements. They're made from the oxyanions. The flow chart says that if I decompose a ternary salt, I'm going to get an oxide, metal oxide, and a non-metal oxide. Let's go ahead and do number 17 first, because you'll see why in a moment. 17 breaks down really nicely. A ternary salt gives us a metal oxide. So here the metal is copper, and it's copper 2. So we're going to have copper 2 oxide. So let's write that formula, copper 2 oxide, which is a solid. And then the only thing left now is a carbon and 2 oxygens. So the non-metal oxide is CO2. That's pretty straightforward. Not easy, but straightforward. Now number 16 is a pain, because number 16 is actually a violation of the rule on the flow chart. You may even want to add this to your flow chart if you haven't been directed to do that in class yet. Chlorates are an exception because they don't break up. So let's just call this chlorates. They break up to give us chlorides and then oxygen gas. So it's just another type of decomposition. So if that's the case, my product will be nickel 2 chloride and then oxygen gas. And then we would need to balance that. I believe I need 3 oxygens there. Did that do it? I think it did. All right, so you're wondering how you're supposed to know all these exceptions, and the answer is you learn them, and you learn through experience. I can't just implant you all these different things. You'll be frustrated as you learn, but that's part of the process. You will not be responsible for crazy exceptions on the test. So just as you practice, appreciate something new when you encounter it, and then file it away in your memory banks. When we return, we will be doing single and double replacement reactions and then combustion.